Hello all, can you hear me?
Yes, we can hear.
So let's wait a minute before we begin. So actually there is no attendance poll today because you're on Zoom, and Zoom tells me exactly who is signed in, and for how long. So I have all the information I need. In addition, we do have the polls. Also, folks, before I begin, during the lecture, I am going to frequently ask you if you have understood the concept or not. And I'd appreciate it if you could give me a thumbs up, which you can on Zoom, or just type yes into the chat box. You're also welcome to ask questions and such like, and or post comments in the Zoom chat box. I won't see all of them, but I'm going to try to respond to as many of them as catch my attention. So with that said, let's begin. We're going to continue our, we have 25 people in the class of 300. Just not, okay. We're going to continue our series of lectures on training neural networks. If you have any problems hearing me, just let me know, right? So here's where we were. Emma, there's no class poll for today. So here's where we were. We've seen that neural networks are universal approximators. We must train them to approximate any function. Networks are trained to minimize total error on a training set, and we do so through empirical risk minimization. And we use variance of gradient descent to do so. So gradients are computed through backpropagation. This is what we've seen so far. We also saw that vanilla gradient descent may be too slow or unstable, and better convergence can be obtained through second-order methods that normalize variation across dimensions. We didn't actually go over this in class, but it was on the slides. Better convergence can also be obtained through adaptive or decaying learning rates that can improve convergence. And methods like rprop that decouple the dimensions can improve convergence. We also briefly looked at momentum methods, which emphasize directions of steady improvement and de-emphasize unstable directions. So we're going to move on from there. We're going to talk today about incremental updates, and we will revisit trend algorithms. In the next class, we will talk about generalization and some tricks of the trade. So first, incremental algorithms. Any questions about all the topics we've covered so far? Any questions?
Hello, Doc.
Yes, you say
Oh, it's me,
something.
Jay.
Okay, so doesn't seem to be any questions. There don't seem to be any questions. So let me continue, right? So here's how we formulated training. You were given a bunch of training data points, which consisted of inputs and the corresponding outputs. And so the function that you wanted to model went through these points, except that the function itself was unknown. And so we trained the function to minimize the error at these training points. The way we did it, you'd start off with an initial set of parameters for your network, which would give you an initial function. And then at each of the training data points, you would have an error as a result. For example, here, this is your error. Here, this is your error, and so on. And the error the loss was the total error, the total divergence across all training points. Gradient descent would adjust the network parameter values to reduce the error, the cumulative error at all training points. So the gradient descent adjusts parameters to increase the function value at these points, to maybe decrease the function value at these points where the current function is overshot, and then increase it again at this point. So this would give you a new set of points at which again you would compute the total error. And then the next iteration of gradient descent would again adjust the function everywhere at every one of these training points by maybe increasing the function value here at the green arrows and decreasing them at the red arrows. And this would keep happening at each iteration. And at each stage, the overall error, the error across all training points would be minimized. So this is what we call a batch update, where we simultaneously compute the total loss, the total error over all training points, and then adjust the network parameters to reduce the cumulative error across all training points. So this means that in order to perform a single update, because we need the cumulative error across all training points, we must process all training points before making a single adjustment. This is the batch update. This is what we actually want to do. So before we continue, I'm going to post a poll. Now, polls today will be posted on Zoom, and you should be able to see them. Can you see the poll?
Yes.
Okay.
Prof, I posted a Pokemon in the chat.
Mm. All right, guys. 15 seconds. Right, I'm going to stop the poll. Can you tell me if the first can... Actually, let's skip the Pokemons. Just answer on the chat box, right? Can you guys tell me if the first option is correct or not? What do you think? The actual loss function we try to minimize requires batch updates, right? What about the second option? Batch updates minimize the total loss over the entire training data. They do, right? Batch updates optimize the actual loss function. Also true, right? And batch updates require processing the entire training data before we perform a single update. True or false? So there's a diversity of answers. Let me go back and let's see the answers, actual answers. The actual loss function you want to minimize is the cumulative error over all training data. So you do need to, that's what batch updates try to perform. And so when you perform batch updates, you minimize the total loss over the entire training data. The loss function itself, the first three statements are just repeating themselves, is the total loss over all training instances, and that's what batch updates optimize. Now, this means, having said this 3 times, that if you want to optimize perform a single step of optimization using batch updates, which is the correct thing to do, you first need to process the entire training data before you can make a single update to your network parameters. This making sense to you guys? This is what we've discussed so far.
I have a question, sir.
Yes.
So just to clarify, the way we approximate the loss is like the average divergence over the training data, and because of that, if we want to minimize the average divergence over training data, then when we update the parameters, we need to update them over the entire training data, right?
That is correct, right? And so can somebody tell me what the issue with this might be? Anybody? What could the issue with this be? Too expensive, right? You'd have to process the entire training data before every single update. So that doesn't make sense at all. Now, what could an alternative be? Anyone? What could an alternative be?
Bitch.
So here's what. Remember, those of you who ever played with modeling clay, you want to make a doll with your clay. And you start out with a lump of clay. And if you really wanted to make the lump of clay into this doll, you'd have to shape it simultaneously everywhere so that it looks like a doll. But that's not what we do. What we do instead is, poke it. You have only 10 fingers, and maybe you use only 2 of those at a time. So you poke it in one place at a time. And anytime you push the putty down at one place, it pops out somewhere else. So you have to do it really carefully. But then doing this, one step at a time can eventually shape the putty into the doll. So we do something very similar even over here. Instead of trying to minimize the error over all the training points all at once, we adjust the function one training point at a time. So maybe pick this training point. And then here at this training point, you find that the current function is underestimating the target function, so you push it up. Then you pick another training point. The same thing's happening here. So now you push the function up here. Now, anytime you adjust the parameters in the setting, you're adjusting the parameters only for the specific training point that you chose. So if this was your training point, you'd be pushing the function down so that it went down over here without really any concern about what happens at other points. So for this whole thing to work, since this is again like the modeling clay, you're pushing and adjusting the target function one location at a time. And so when you do this, eventually, once you've done a complete pass over all of the training data, you would have sort of adjusted the function at every single training instance. Nonetheless, for this to work, once again, this is just like your modeling clay, right? You'd have to make sure that when you adjust the function at any given location, the changes at other locations remain small enough that the entire thing doesn't go out of whack. So you have to keep the adjustments small. And so when you do this, well, if you processed all the training points, you would eventually have adjusted the entire function over all training points, potentially with greater overall adjustment than if we had made a single batch update. Did this make sense? What I just said so far. Right. And so, okay. And so here's where we are. Here's what we do, how we perform a batch update. Earlier, you went over all of the training data. You accumulated the gradient over the entire training data and then made the adjustment. Now, after each training instance, you'd be computing the derivative of the divergence for that training instance and making an immediate update to your network parameters. So the iterations, of course, can make multiple passes over the training data. So a single pass over the entire training data is called an epoch. So an epoch over a training set with t samples would result in t updates of parameters, because after each training sample, you would update your parameters. So going back again to our pseudocode, within each epoch, so this do is over multiple epochs, you'd be going over your entire training data, and for each training instance, you'd compute the derivative of the divergence with respect to every network parameter, and then you would be updating the network parameter using gradient update. So a single update is an update of the network parameters after a single training instance, and one epoch is the cumulative updates over the entire training data. Is clear to everybody? Yeah. Just give me a yes so I can continue, right? Okay. And so now to do this, you have to be careful about some things. First, let's consider that these are our training samples. We have 4 training samples to the extreme left, 4 training samples to the extreme right, and for some reason, our network is such that it can only learn a mild curve. It cannot learn a horizontal function. So now, if I start looping through the training data from the left, as I pass over the first 4 training data points to the left, what will happen to the curve? As I adjust it's going to go down where? Where will it go down? On the left. So processing these 4 guys is going to push the function down here. But that made it pop up to the right. So now if I move to the right and begin adjusting the function to the right, what would happen to the function? If I began adjusting it to the right, the left would pop back up, right? And so it's going to begin seesawing. This is not a good thing. So how could you fix it? Anyone? So the way you would do it is to do this randomly. You must go through the training. If you loop through the samples in the same order every time, you can get cyclic behavior. So you have to go through them randomly to get more convergent behavior. Maybe pick one data point here and adjust it. Then pick another data point to the right and adjust it. So long as you keep doing this randomly, you make sure that you're not getting cyclic behavior, and then there is overall correction of the function. So what this means is that now selecting your training points randomly is the same as shuffling your entire training batch, training data. So within each epoch, before the beginning of each epoch, you want to randomly permute all your training data so that when you go back through the training data, they are in random order compared to the previous iterations. This makes sense to everybody so far? Okay. So the story so far,
Good question,
in
sir.
any gradient, yeah.
If you loop through them in the if you loop through all the points in the same order, like would the behavior be like say similar to like just if you had updated like batch style? Like if
No,
you had
no, it would
updated
not, because you're going through this sequentially. So you would get this kind of, you're likely to get this kind of seesawing behavior that I just showed you. So if you keep going through the training data in the same order every time, you won't necessarily get convergence. It can keep bouncing up and down. You must permute the data set across epochs.
all right.
Right. And so the story so far, in any gradient descent optimization problem, presenting the training data instances incrementally can be more effective than presenting them all at once, provided the training instances are presented in random order. And so because we're presenting them in random order, that is in stochastic order, the procedure is called stochastic gradient descent. So is this better? Can you see my entire face? Oh, okay. So now this business of stochastic gradient descent is not specific to neural networks. This is true for any function optimization problem. But in our context, this is specific. This also holds for training neural networks. Now, why does this process of incremental updates work, and under what conditions can it work? For the why, first I'm going to consider a very simplistic explanation that's often given using an extreme example. Again, guys, if you don't understand anything, just interrupt, okay? So let's look at what happens when you update the network using batch gradient. So when you're performing a batch gradient, the gradient that you use is the average divergence, is basically the transpose of the average divergence over the entire training set. So it's basically the average of the gradients for the individual training instances. Now the individual training instances now each individual training instance has a divergence function that responds somewhat differently to changes in network parameters. So consequently, the gradients that you observe from the individual training instances will all point in different directions. The actual gradient that we use to adjust the network parameters is the average of all of these guys, which might be, so for example, these little blue arrows might represent the individual divergences for the individual training instances. The average might be something like the orange arrow. That is what you would use to adjust the parameters. This is your standard batch gradient descent. Is this picture making sense to you guys? Yes or no? Okay. So now let's consider an extreme case where I have many training instances, but all of them are exactly identical to one another. So I have data clotting. All the training instances are exactly the same. Now, in this case, after I've gone, will the gradients of the divergences for the individual training instances be different? If all the training instances are identical, will these guys be different? No. So what will this average be? what will this average be? It's basically going to be the same as the divergence for a single instance, right? And so now what this means is that if I used batch gradient descent, the update I would get after processing all of the training instances is going to be the same as the update I would get if I just updated my network parameters after a single training instance. Whereas if I perform stochastic gradient descent, although the actual step size may be smaller, because I keep updating the parameters after each training instance, after a single pass over all the training instances, the network can change a whole lot more than it can in the batch case. Is this making sense? Guys, so waiting for any responses. Okay. And so that is the extreme case. Now, suppose all of the training data points were not exactly the same, but just a little bit shifted with respect to one another. Would you expect the same logic to still hold? Yes or no? Right. And so when would this logic kind of break down? Anybody? When would the logic break down? If they are very, very different, right? As the data get increasingly diverse, the benefits of incremental updates kind of decrease, but the fact is they don't entirely vanish. So we've sort of seen why does it work? When does it work? And what are the considerations? And how well does it work? So for why, first let's take one of the more common issues. Here I have a simple problem. I'm trying to fit a regression line through all of these data points such that the perpendicular projection onto this line has the smallest error. Basically, I want to find a line of this kind such that when I project all the points onto it, the error, which is the length of these, total length of these thin lines, is minimized. Now, I can do this in batch where I look at all of the training data all at once and perform PCA, or I can do this one data point at a time. So if I just looked at this one data point, right, say this one, then what is the line? And I'm going to constrain that the line, impose the constraint that the line must go through the origin. So now if I consider just this data point, what is the line that gives me the lowest projection error? That's going to be the line that goes directly through that data point, right? Then I pick another data point, say this guy. And then I adjust the line so that it passes through that data point. It's going to swing around over here and now pass through this data point. Now I pick another data point, right? And although I'm picking the data points randomly, each time I pick a new data point, the line is going to keep swinging towards the latest data point. So will this process ever converge? Right. So what could a solution be? Anyone? What could a solution be? Move it. These are, so here, the solution is you want to shrink the learning rate with iterations. And so that way, with increasing iterations, it will swing less and less towards the new point. So for example, maybe for the first instance, it goes right through this point. Now the next instance is out here, but instead of swinging all the way to this guy, you go only part of the way to it. Then for the next instance, instead of going all the way from here to this, you go towards it, but the step size is even lesser. So if you keep adjusting, but swinging less and less, if you shrink the learning rate with the iterations, eventually, when you've seen enough data points, the learning rate would have shrunk so much that the newer data points will not make the line swing around a whole lot, and the whole thing will converge. So the requirement over here is that the learning rate must be reduced as we process the data, as we go through the data.
Question, sir.
Yeah.
So the general idea is that, like, in this example, like, we kind of like want to move the line towards each new point. But the way that it converges is that like as you increase the iterations, it becomes less and less sensitive to each new point. Eventually, it doesn't. At that point, it converges.
That is correct. And Adi, what if the first point are outliers? It doesn't really matter. So long as, in the end, you're seeing all of the data points. And if you continue with it long enough, it will converge. But then, you have a valid question, right? What if the first points are outliers? So can you think of some criteria that will make sure that Adi's question is answered? Anybody? Let me explain, right? So let's say this guy here is my optimal solution. Let's say this is where I begin from. Now your learning rate is going to be, your updates are going to be eta times d divergence by dw, right? So let's say that your divergence function is kind of nice. And so this derivative has an upper bound. So I can just say that the derivative of divergence with respect to any weight is always less than or equal to some upper bound c, right? So then what is the largest amount by which a single iteration can change the value? Anyone? What is the largest amount by which is eta c, right? So the largest amount that it can take is eta c, right? Or if the iteration step sizes are changing with iteration, it's eta ic. So this guy is eta ic, right? Now, if I keep taking steps, eventually I would like to get all the way to this point, right? What is the largest amount by which the total increase can be? That's going to be assuming infinite steps, I equals 1 to infinity, eta c, right? The total correction is going to be less than or equal to this. You agree? Yes or no? Okay. Well, how far away could you be from the solution in the worst case? How far away can you be from the solution in the worst case? Anybody? You can be infinitely far away, right? So that means you want delta W to be potentially as large as infinity, right? C is bounded. So what is the condition on eta as a result? If this guy can go to infinity and this is bounded, then what is the condition on eta? Anyone? Eta shouldn't go to infinity, but you want summation I equals 1 to infinity of eta to be infinity. Is this making sense to you guys? Right. So over infinite steps, the learning rates must sum to infinity. If that is guaranteed, then it doesn't matter how far away you begin, eventually you're going to get to the solution, right? That makes sense to you? Yes or no? Okay. At the same time, you want eta to decrease with iterations. So it turns out that we have two criteria. The first criterion is this. You want the, okay, so this is your updated learning rate, pseudocode. You'd still want to permute your training data instances between epochs. But then this learning rate reduces with j, and specifically, you want this condition to be satisfied. The sum of the learning rates must be infinity. At the same time, the learning rates must converge, which means they must keep shrinking. So the second criterion, it turns out, is that the sum of the squares of the learning rates must be finite. So this ensures that you can traverse infinite distance. This ensures that they keep shrinking, and so the whole thing will converge. Is this making sense to you guys? These two conditions. So wait, are you having trouble hearing me? What about now? Any better? Something happened to the mic. I'm not sure. Let me see. Nothing should have happened to the mic. Let me audio settings. Is this better?
Yes.
Oh. So the volume seems to have gone down on its own. Okay, anyway, is this making sense? This pair of conditions. Okay. So can anybody tell me of a series that is not absolutely summable, meaning when you sum them up, it goes to infinity, but it's square summable. When you sum the squares, it's finite. 1 over n, right? And so the condition that you have, 1 over n, the sum of it, so the sum of the series is infinite, but the sum of 1 over k n squared or 1 over k squared is finitely summable. So it turns out that the fastest converging series that satisfies both of the above requirements is this guy. And so you also have this requirement that the learning rate must be roughly proportional, or at least the hull of the learning rate must be proportional to, if k is your iteration index, 1 over k. And so it turns out that in pretty much all of the learning rate schedulers that you use in your actual life, at some level, they will satisfy these two conditions. That they're kind of that the absolute sum of the absolute values can be very large. At the same time, they're square summable, and they'll roughly have a hull of around 1 to k, 1 over k. So let's assume that both of these conditions are satisfied. So the learning rate converges. At the same time, it satisfies this property. Then and all the other criteria that we are randomizing our training instances and so on. How does it work? Here's an example. In this case, I'm not training a neural network. This is a k-means example that I got off the web. We have a bunch of training data, and they're trying to cluster the data points using k-means. Now, again, depending on the initial values for k-means, you can get different solutions. So this green line shows you how the total error decreases with iterations for k-means. And the vertical bar shows you the variation across runs. This red line shows you the same thing, except now they're using stochastic gradient descent, where they are updating the parameters after each training instance. What do we observe? Is SGD faster than, so this is full batch. This is stochastic gradient descent. Is SGD faster than full batch? Yes. But does it get to the same optimum? No. What else do you observe? What else do you observe? That this variance is very large, right? So it turns out that, yes. Okay, first, let's actually answer this poll. Can you see the poll? Okay, 15 seconds, guys. You got most of it. All right. Is that first statement true or false? It's true, right? What about the second one? True or false? What about the third? Also true, right? And the fourth? Also true. So all statements were true over here. SGD is an online version of batch updates. It can have oscillatory behavior if you do not randomize the order of inputs. It can converge faster than batch updates, but arrive at poorer optima. And SGD convergence to the global minimum can only be guaranteed if step sizes shrink across iterations, but sum to infinity in the limit. So that's the behavior of SGD. Now let's try to understand it. And we're going to understand this. We're going to use a little bit of math. Now, first, if you go back several classes, you'll remember that what we actually wanted to minimize was this guy. This was the integral of the error, the divergence between the network function and the actual function that you wanted it to model, weighted by the probability of the input. So this term inside the box was the expected value of the divergence between the network output and the true output. And so we'll get to that answer. So this is what we wanted to minimize, right? That's what you would be adjusting the network parameters to minimize. Do you guys remember this? Yes or no? Okay. Now, do we actually minimize this, or do we minimize something else? What do we minimize? You minimize a proxy to it, which was the average divergence over the training data points, right? But then it turns out that if I take the expectation of this one, the expectation of the loss on the left-hand side is going to be the expectation of this guy here, right? And through the linearity of the expectation, which is this equals 1 over n summation expectation of the divergence. Now, the expectation of the divergence doesn't depend on x itself. So this is simply going to be 1 over n times the expectation of the divergence. And the n's cancel out. So it turns out that the expected value of the loss ends up being exactly the objective function that you actually wanted to minimize. What does this mean? It means that, for example, if I were to get 1 million training data points, if I looked across all possible sets of million training data points, and I computed the losses over 1 million training data points over all of these infinite different sets of million training data points, the average across all the sets of the loss would be the true objective function. It is the expected divergence that we are trying to minimize. So it's a statistical kind of statement, but then we often use it to justify our use of a loss rather than the actual expected divergence. Did that make sense to you guys? So what does it mean to take? So think of it this way. When I take the expectation of the loss, it's like taking, let's say if I had 100 training data points, I've chosen a random 100 data points, right? What is the divergence on any one of those? Again, treating it as a random variable. If you don't know x, if I take an expectation, it's just the expectation of the divergence of a random variable xi, which is simply this guy itself. If I don't know the positions of these guys beforehand, I treat each one of them as a random variable, which is the same as x. Did that answer your question? Okay, whose question was it? Somebody asked. Anyways. Okay, so now here's the other thing. So this is our reason for using the loss. But then now suppose I have two variables x1 and x2, which are statistically independent, right? So and I have, if I define y equals x1 plus x2, then what is the variance of y? Those of you who have done your probability can tell me, right? Let's say I know the variance of x1, I know the variance of x2. Y is the sum of x1 plus x2. What is the variance of y? Anyone? This is the variance of the sum, right? It's the sum of the variance. It's the variance of x1 plus variance of x2, correct? Now, suppose I sum n of these guys. So if x1 and x2 have identical distributions, that is simply 2 times variance of x1, variance of x, right? This making sense to all of you guys? Yes or no? I see one person saying it. Okay, suppose I sum n of these guys, x1 through xn, and all of them have the same distribution. What is the variance of the sum of n variables, these n variables? It's n times var of x, right? Now, suppose I take the average. Instead of simply summing them, I divide by 1 over n. Then what happens? If I take the average, multiplying a variable by anything is the same as when you multiply any variable x by some constant alpha, the variance of x is multiplied by alpha squared. Because the variance is actually a squared thing, right? Squared term. So this is going to be n times variance x over n squared. So which means when I take the average of n variables, the variance of the average is going to be variance of x divided by n, where n is the number of samples I've taken. Is this making sense to you guys? Yes or no? Okay. And so this sort of explains a lot of what we just saw happening. Here, when I take a loss over n training samples, the average loss over n training samples, first, the expected value of the loss is the actual objective that we want to minimize, which is why we call this an unbiased estimator. And so we have some reason to believe that minimizing the loss will also minimize this term to the right. But then we have a second reason to believe in it, that the variance of the empirical risk is 1 over n, the variance of the divergence for a single instance by itself. The larger the variance for a single instance, the greater the likelihood that the parameters you estimate will differ significantly from the true optimum. Now, this kind of doesn't make a lot of sense when you're talking math, but we'll see some pictures which might clarify, right? Now, but then let's consider SGD. At each SGD, now when you're going through stochastic gradient descent, within each iteration, you're minimizing the divergence for only one training instance. This is what you'd be minimizing, right? Because SGD is only picking one point at a time. So the expected value of the loss that you minimize at each step of SGD is still the expected value of the divergence, which is this guy, which is actually the objective you want to minimize. And so it turns out that even when you're performing SGD, the sample divergence that you get is an unbiased estimate of the expected error. So which is why you have some reason to believe that SGD will take you towards the optimum. But the thing is that the variance over here, the number of samples you're averaging over, which is n, is 1. So instead of getting 1 over n times the variance, where n was the training sample size, here the variance of the loss is the variance of the divergence itself. And this tends to be much, much larger. So it's 10 times the variance of the empirical average, minimized by batch update. And that's why you saw the behavior that you just did. Now, did any of that math make sense to you guys? I'm expecting a few of you to say yes. I'm expecting everybody who said yes to be kind of waving their hands, because it didn't really make sense to me either the first time I saw it. So let's go back and look at pictures, right? Here's what it is. Let's say the blue curve is the function you're trying to estimate. Let's say the red curve is the current estimate of the network, from the network, right? Now, if I have a bunch of training data points, the actual error that you're minimizing is the total length of these solid lines, right? And now, if I look at the total length of these solid lines, it's going to tell me that the function must be, I'm looking at batch updates. It's going to tell me that the function must be pushed up to over here. It must be pushed down at these 3 locations, and it must be pushed up here. I have 6 training samples. But then, if I choose a different set of 6 training samples, say like this one, then the answer I'm going to get is very different. It's going to tell me that the function is either correct or always underestimating, because at all of the training samples, the red curve is below the blue curve. And so the advice that this training set is going to give me is to always push the function up. On the other hand, if these were my training points, then you're going to find that at a majority of the training points, the function is overestimating. The network is overestimating the true function. And the advice that the training samples are going to give me is to always push the function down. So depending on where this training samples fell, you're going to get a completely different advice from the training data for the same network. Is that making sense? Right. So this is the variance. Depending on where the training data points land, the loss function is going to give you something very, very different advice. What would be one way of improving on this? Of anyone? Can you suggest how I can get around this? Anybody?
You can spread the points always, the training points.
If I have a lot more training points, more samples, if I have a lot more training points, then the odds that cumulatively the training points are going to change the advice they give a whole lot from sample to sample is going to be much smaller, right? So having more samples makes the estimate more robust to changes in the position of samples, which means the variance of the estimate is smaller. This answer your question? Answer my question? Did this make sense? Yes or no? Right. So Daniela, this has nothing to do with normalizing the data. It just means that, regardless of whether you normalize it or not, the size of the space is, more or less the same, right? So let's see what happens with SGD, right? With SGD, you have only one sample. If the sample happens to fall here, you're going to say, oh, my network is fine, right? On the other hand, if my sample happens to fall here, you're going to say, I'm underestimating. I must push the function up. If it happens to fall here, you're going to say, I'm overestimating. I'm going to have to push the function down. So the problem with SGD is that the advice you get from that one sample you get can swing wildly depending on the sample that you chose, which is why if you look at this, when you do batch updates, the variance across batches is actually across runs is quite small. Whereas with SGD, you change the loss from update to update, and the loss can swing quite widely, right? Which is why you get this very large variance. That clear to everybody? Having more samples. So Victor, what does this picture tell me? Over here. Will the total loss be more in this case? Will the variance of the loss, the average divergence, be more in this case or in this case? What do you think, Victor? Just looking at the picture, which would be larger? Anybody else want to answer that? Less in the case of more samples, right? Because even if you have many more samples, even if across many different, you have many more runs, because you have so many samples, they're going to cover most of the distribution. Whereas if you have fewer samples, the variance from sample to sample can be very large, which is what explains this behavior. And so SGD uses the gradient from only one sample at a time, and therefore it has very high variance. At the same time, it provides significantly quicker updates than batch. So is there somewhat of a medium where we get the faster convergence of SGD without getting the increased variance of SGD? And so this is exactly it. Instead of just picking only one point or all of the points, you combine the two concepts. Adjust the function at a small, randomly chosen subset of points, keeping the adjustment small. If the subsets cover the training set, eventually you've adjusted the entire function. As before, we must vary the subsets randomly in different passes through the training data. So your first update might be, say, on these 3 points. Then you update the network according to the error here. Then your next update may be at these 3 points. Then you'd update accordingly, right? And so each time we're working on not one point, but on a subset of points. It's what you call a batch size. And so now you'd be accumulating the gradient over this batch or this mini batch. And you'd be using this cumulative gradient over the mini batch to adjust your network parameters. Now, is this making sense to you guys? Right. Okay. So now let's look at the math of it, right? We saw that if I have n training points, then the variance of my loss was the variance of, I'll call this d of x, the divergence divided by n. So if n was my entire training set, this would be some size. If n is just 1, as in the case of the stochastic gradient descent, then the variance is just going to be this term itself. So let's see how the variance changes with mini batch size. If this is my entire training data, then this guy is about as low as your variance can get, maybe something out here. For n equals 1, maybe you get something out here. That's your variance. And then as your mini batch size goes down, you're going to find that this variance falls off as 1 over b, right? And so there's a knee of the curve where you get almost all of the way down to this guy while keeping the mini batch size small. And so this point, you want the mini batch size to be as large as possible, but 1 over b falls off like so. And you want to choose a b such that the gap between this and this is as small as possible, so that working with that mini batch still gives you the same kind of behavior as you would get with the entire batch. That makes sense? Yes, no? Okay. And so this is where we stand, right? So again, now we're going to be operating over mini batches. The rest of the rules still hold. You still want to randomly permute the input across epochs. And you still want the shrinking step size, because although you're working with mini batches, the mini batches are not the entire training set. And so you still need all the usual guarantees. But if your updates satisfy all these conditions, then you're much more likely to get to a proper solution. So again, the mini batch loss is the average divergence over the mini batch. The expected value of the mini batch loss is also the expected divergence. So the mini batch loss is also an unbiased estimate of the expected loss. And the variance of the mini batch loss is 1 over b times the variance of the divergence for x. So for Ayush, if I have 1 billion data points, then you'd have to process all billion of them before each update. We saw that early on, right? So you want to make your updates after processing the smallest number of data points that you can get away with. 1 is too small. The entire training data set is too large. So we choose something in between, which is B, right? So Yulin, n doesn't matter at that point, right? You just choose B. And so here's how in our previous example, the whole thing behaves. This was the batch update. The orange was the stochastic gradient descent. The blue was the mini batch update. And we observed that the mini batch update converges to basically the same loss as the batch update with a variance that's comparable, but it converges as fast as the stochastic gradient descent itself. This making sense to everybody? Yes, no? Okay. And so now again, in this particular example, they actually process the entire training data set after each update just to compute the loss, right? Because when I'm speaking of convergence, and speaking of convergence in terms of the loss over the overall entire training data, in your homework, you actually plot the loss on the latest mini batch. So these behaviors are not guaranteed for the latest mini batch. So you're likely to see some strange behaviors. Nonetheless, the hypothetical loss over the entire training set is likely to have a much more convergent behavior than the loss on your mini batch. So in practice, training is usually performed using mini batches. The mini batch size is generally set to the largest that your hardware will support without compromising overall compute time, because larger mini batches means less variance. Larger mini batches also means, however, fewer updates per epoch. So these two are kind of a bit of a trade-off from one another. And then convergence still depends on learning rule. You want the learning rule to be to sum to infinity, but to have a finite square sum. So a standard typical method is to fix the learning rate until the error plateaus, then reduce it by a factor and keep doing this. And regardless, you will find that the learning rates that you choose satisfy this behavior that the absolute sum will be large and the square sum will be finite. You can also have adaptive updates where the learning rate itself is determined as part of the estimation. We'll see that in the next few slides. Any questions? Did all of this make sense so far? Okay, so let's go to our next poll. All right, 15 seconds. Let me stop this. First statement, true or false, guys? It's true, right? You can keep making updates as the data come in. Second statement, true or false? False. Mini batch descent. SGD is basically mini batch with a batch size of 1. So they would be identical. The variance decreases with batch size. True or false? True. And mini batch descent approaches batch updates in variance, but SGD in efficiency. True or false? Also true, right? Very nice. And so that's what we would use. Questions?
I have a question.
So,
Why is the third? Why is the third point correct? Didn't we say that larger mini batches led to less variance?
That's exactly what it says. The variance of mini batch updates decreases with batch size. Decreases with increasing batch size. That should be better stated, right?
Okay.
Right.
Thank you.
Okay, so yeah, I should fix that. So SGD, presenting training data instances one at a time, can be more effective than full batch training. But that's a story so far. For SGD to converge, the learning rate must shrink sufficiently rapidly with iterations. Otherwise, the learning will continuously chase the latest sample. SGD estimates can have higher variance than batch estimates. Mini batch updates operate on batches of instances at a time. And so the estimates will have lower variance than SGD. Convergence is theoretically worse than SGD. I've not gone through the theory, but because you can perform batch processing overall, it ends up being much better. So now one of the issues that happens with SGD and mini batch is that the loss function that you minimize, the loss function itself changes from mini batch to mini batch. Do you see why this is true? Why does the loss function change from mini batch to mini batch? Anyone else? Why is this change from mini batch to mini batch? You have different training samples in each mini batch, right? So this means that the objective that you're changing keeps moving around all the time. And so you have crazy behaviors. Even if you're doing the perfect job within each mini batch, the first mini batch may say you want to correct the parameters this way, but then the next mini batch may say you want to correct the parameters this way. The estimates that you have can keep swinging around quite widely. And so the problem that we had earlier where we said that, for an objective function, you can have jittering or even divergent updates. That becomes exacerbated in the case of mini batch and stochastic gradient descent. So, Shiva, it's not just that the data will be noise, the data are themselves different. So the function is fundamentally different. The loss is being computed on a different data set for each mini batch, right? And so in this case, it becomes much more important to make sure that you sort of handle this business of the gradients swinging around wildly from mini batch to mini batch. And so here, instead of just following the gradient of the latest mini batch, if you want to get an estimate for the gradient over the entire training data set, rather than just the gradient on the latest mini batch, you have to use some kind of a running average. That makes sense? To you guys? Why the running average is more important in this case? Right. Because when you maintain a running average, you're averaging the gradients computed over the mini batches, which is going to approach the gradient over the entire training data set, which is the actual objective function you want to optimize. And now the thing is, what you would use at each point after the kth mini batch is the g hat k, which is 1 over k summation gk, where gk is the gradient after the kth mini batch, right? Or I equals 1 to k. This is what you want to actually use. This is the running average. This formula making sense? Yes or no? Okay. But then I can write this as k, this is k over k minus 1, summation I equals 1 to k minus 1 gi plus 1 over k gk. I just pulled out the last term over here separately. And so this, wait, no, it's k minus 1 over k, I'm sorry. I just pulled out the last term separately. Let me erase this and write this properly. I can write it like so, right? Yes or no? These two are the same. Unclear? Let me try writing this again. So is this formula to the left making sense? This as the running average. Is this making sense? This guy. Okay. So let me just separate out, that is summation I equals 1 to k minus 1 gi. It's still 1 over k plus 1 over k gk. Do you agree with this? Yes or no? I can multiply and divide by k minus 1. Right? Yes or no? Okay. And this guy, 1 over k minus 1 summation over the first k minus 1 terms is just g hat k minus 1. So I can write g hat k equals k over k minus 1 over k g hat k minus 1 plus 1 over k gk. This is my running average. The current running average is a function of the previous running average plus the latest sample. Is this making sense to you guys? Yes, no, yeah, okay. And so this is the formula we will use. We have a minus eta over here because we factor the step size in. But basically what we are doing in your momentum method is to maintain a running average of the gradient of actually the negative of the step size times the gradient. It's factored in. and you always update the network parameters using the running average of the gradient. This has the advantage of not only canceling out wild swings in the wrong directions, but also smoothing across many batches. This making sense to all of you guys? Okay. And of course, yes or no, guys? Can you give me a, okay. And then we also, so this is the momentum method. If your current correction was this one, and the next mini batch correction told you to go this way, then you'd be averaging the two, the gradient at the current point plus some beta times the previous step, and that's going to be a correction. We also saw that this can be improved upon using Nesterov's method. How did we change? How was Nesterov's method different than the momentum method? Anybody remember? How was Nesterov's method different? Anyone? We changed the order of the two steps. So in the gradient descent from the current point, you took a step against the gradient and then added in a scaled version of the previous step to get the correct current update. In Nesterov's, so this was step 1 and step 2. In Nesterov's method, you first took an additional step in the direction of the previous gradient, and then you computed the gradient at that point to get the new update. And it turns out that changing the order actually gives you something more optimal. So regardless, so here you have formulae. You have computing the gradient at a location which is the k minus 1th value plus some beta times the previous step. And this is being added to the previous step plus this point, right? So that's basically what you would get. Anyways, and we saw that in the last class that actually gives you faster convergence. All that is fine. So the whole point over here is that momentum and Nesterov's method are using some kind of a running average of derivatives to smooth out innate fluctuations in the gradient because of the nature of the loss function, but also extrinsic fluctuations that come from the fact that each mini batch is looking at a different loss function. So momentum smooths out the variations and you get faster and smoother convergence. So this was Nesterov's method. And so here's where we are. Here was the standard gradient descent rule. You had a current estimate. In your standard gradient descent rule, you would compute the gradient at the current location and then take a step against the gradient, right? The momentum methods fixed this guy. And by fixing this guy, they got rid of some of the fluctuations that you could get by just following the derivatives, the gradients, right? This making sense over here, what the momentum methods just did. Is this making sense, guys? Yes or no? Okay, is there anything else over here that you see that can also be modified to improve things? What else here can be modified? Anyone? The learning rate, right? I can fix this guy. And how can I fix this guy and why must I fix this guy? Let's take a look. So let's say I have these three cases, this blue curve, and each arrow represents a gradient at a current estimate, right? So let's say I have this sequence of gradients versus this one versus this one. Now, if I consider the running average for the vertical direction in all three cases, are they going to be wildly different or are they going to be more or less similar because the upwards and downwards keep canceling each other out? What would happen in the three cases? Would the running average in the vertical direction be comparable in all three cases? In all three cases, the running average is going to be the same, right? So should I be using the should I be using the same learning rate in all three cases? Or is one of the cases less trustworthy than the others? What do you think? So over here, if I have a learning rate of 0.1 in the vertical direction, would have a learning rate of 0.1 in the vertical direction over here also make the same sense? Or should it be lesser over here? Okay, so we agree that this really requires a smaller learning rate. What clued us in? What clued us into the fact that this guy deserves a lower learning rate? Anyone? The total movement is large, but the net movement is small, right? So any direction in which the total movement is very large probably requires lower learning rate, right? Highly oscillatory behavior. And so here's what we would do. So what would be indicative of the fact that it's swinging a lot without gaining much? The second moment over here, the variance in reality, but this is very high variance compared to this, but just the second moment would also do. And so that leads us to RMS prop. RMS prop, this is done independently for every parameter. By the way, so when I write partial d, it really represents a parameter. When I say partial square d, it's not the second derivative, it's the square of the parameter. So just for notation, right? And so what we want to do is we want to scale down the learning rate for which the average squared derivative is large. Because if the squared derivative is large, look over here. Although the average derivative is canceling out in the positive and negative directions, if I take the squared values are going to be much larger for this guy than for this guy. Yes or no? So that's what we're going to use. What we do is maintain a running average of the squared derivative in each direction. And then the learning rate, we have an initial learning rate, and then we're going to scale it down by the root mean squared value of the derivative for each direction. And the root mean squared value, again, it just means you're saving one extra term for each parameter, which is the running average. So it's not a lot of overhead. But by scaling it down like so, it means that you're also directions in which you get a lot of movement end up with a lower learning rate, whereas directions in which you have small steady movement get a larger learning rate. And so the learning rate itself adapts to the total movement in any direction. This making sense? Over here? Okay, can anybody see the relationship between this and R prop? So in R prop, did we consider the actual value of the derivative or just the sign? What did we do in R prop? Only the sign. Now suppose I had a steady slope, a flat surface. What is this guy going to be? This is going to be constant, right? This term is simply going to be partial d, correct? Because this is the same from step to step if I have a flat surface with a steady slope. Yes or no? Right? If I have something which is just straight like so, the slope at every point is the same. So the RMS value is going to be the same as the derivative itself. So these guys will cancel out. And so when you have a steady slope, this just reduces to R prop. Or it reduces to a term that completely ignores the actual value of the derivative, regardless of the derivative itself. So in that sense, it looks like R prop. And so RMS prop was originally proposed as some kind of a development over R prop, which is where this terminology comes from. But is this whole process making sense to you guys? This one. Yes or no? What we did here. Okay. And so here we are, right? clear this. So, we fix this guy for momentum methods. We fix this guy for our RMS prop, right? Momentum only adapts the green, RMS prop only adapts the yellow. What's the obvious next step? Anyone? Combine the two. Do you agree? Adapt both, right? And that gives you Adam, right? How about we combine both? And so this is Adam, which is basically RMS prop with momentum. RMS prop only adapts the learning rate. Momentum only smooths the gradient. Adam combines the two. You maintain a running estimate of the mean derivative for each parameter. You maintain a running estimate of the mean squared derivative. The learning rate is proportional to the inverse of the RMS derivative. And so this is what we're actually, this is basically just momentum plus RMS prop. Making sense? Yes, no? Right. It's kind of obvious, right? Once you think about it, it's very neat. There's nothing magical or fancy about it. It's almost obvious. Now there's this extra one minus delta raised to k. This guy here, this is basically an engineering hack, because anytime you use running averages, typically the way you would do this is that you're going to set this delta close to 1, right? If you set delta close to 1, then in the initial iterations, at least 1 minus delta is going to be close to 0. And so your running average will not change, because the second term is hardly ever going to actually influence the mean. So to try to ensure that the running average actually adapts faster in the early iterations, we have this extra term, which is divided by 1 minus delta raised to k. So for when k is 1, k is 1, then this guy over here is basically this gets cancelled out, and you make faster updates in early iterations. But that's just an engineering solution. Okay, I'll skip that. So any questions so far? Any questions? None? Was all of this clear? Yes or no? Okay. And now, so there are many other variants of the same theme. If you understand Adam, you've understood them all, right? They're just minor modifications. You have add a grad, add a delta, add a max. They're all kind of different variations of this basic idea. The nice thing over here is that there's generally no explicit learning rate to optimize, because the learning rate is kind of factored in. But you do have other hyperparameters, like what is eta? For RMS prop, eta is typically 0.001. You have gamma, which is the running average term, which is typically set to 0.9. For Adam, we have a running average term both for the mean and the variance. So those have to be updated. And it also turns out that eventually sometimes you still do need to use a schedule. And so here's the last of our polls. Okay. Okay, 15 seconds, guys. 5. First statement, true or false? What do you think? Does vanilla SGD consider long-term trends? Does it? It's false, right? Vanilla SGD does not. What about the second one? Momentum methods, do they consider the long? Yes. RMS prop only considers the second order moment, but not their average. True or false? True. Adam considers both? True. Right. And trend-based optimizers are important to smooth out the variance of SGD or mini batch updates. Also true, right? So this guy, the first statement should be wrong. That should not be highlighted. Now, out on the web, so there's this guy who's Alec Radford, who plotted how all of these different techniques work for different functions. This is Beal's function. And you can see that SGD is really slow. And this doesn't have Adam, but had a grad, added delta. They're kind of similar. RMS prop takes its time, right? You can just see SGD just gets stuck. All of these other methods tend to be much nicer. And momentum and Nesterov's, because they're just following the trend, local trend, without considering the oscillations, they tend to wander off, but then get there very quickly. Here's a nicer one. You can see how SGD basically gets stuck in the saddle point, where the rest of them eventually make it the right way, right? Or here's another one where SGD takes its time, but the rest of them actually make it to the solution much faster. So, you can, very nice visualizations. You can find many more on the web. Anyway, stopping here. So what the story so far is that gradient descent can be sped up by incremental updates. Convergence is guaranteed under most conditions. Learning rate must shrink with time for convergence. Stochastic gradient descent updates after each observation. This can be faster than batch learning. Mini batch updates after batches. This can be more efficient than SGD. And convergence can be improved using smooth updates like momentum, RMS prop, and Adam. So we'll stop right here. First, did today's lecture make sense to you guys? Yes or no? Final question before I let you go. Okay, thank you. I'll be here for a few minutes for questions. Otherwise, thank you for turning up on Zoom. I appreciate your time. Let me stop recording.